Okay, so our next speaker is Guillermo Mantilla-Soler from Universidad Conrad Lorenz and Aalto University. And he's going to be speaking on a tour of arithmetic invariance of number fields.
Okay, thank you, Frank, Anindam, Padma, David, and Jenny for the organization of this conference. Thank you for the invitation to give a talk in pajamas. This is sort of my first time, and I'm so happy to be here. Anyhow, so just a warning about my talk. So I'll give you a bunch of results and a bunch of things that I care about. But I should mention that the way that I like to talk about math is not sort of showing results and kind of having the proofs, but more like having the sort of how did I get to those results? What is the thought process? So what I'll try to convince you is why these results are important, or at least important to me, why I thought about it the way I thought about it, and how to get there. And in certain specific cases, I'll mention the tools that you usually apply when studying these kind of things. Okay, so arithmetic invariance. So what do I mean by an arithmetic invariant? So this is sort of an informal definition, right? This is something more like for what experience tell me what it is. So we'll try to guess what it is. So it should be something like this. You take a number field and you assign to the number field an object, okay? Some type of mathematical object. And we want this to be an invariant in the sense that if you have two number fields that are the same for us, i.e. isomorphic, then the invariants are the same, whatever it means for them to be the same. So it could be two numbers and the two numbers are exactly the same number. It could be a group and then the two groups are isomorphic, or any sort of notion of the same. Now, the important question is, what do we want when we say we want them to be of arithmetic nature? So algebraic number theory, so we would like those invariants to care about the factorization in the Greek of integers, right? So that's what we usually mean by we want something arithmetic, at least in algebraic number theory, something that cares about the factorization. And we want invariants that are awesome in a sense. What does it mean to be awesome? An invariant is like, so the mathematical term is complete, is an invariant that tells me everything. So like a function, if it were a function, would be a one-to-one function. But as experience will tell you, that might be asking a little too much, right? We are just putting us in a corner if we ask for this kind of stuff. So we will just say, okay, maybe just care for invariants that are, they have finite fibers, meaning that if you have as the quantity shared by those number fields is only shared by finitely many of those, okay? At least this is sort of some informal conditions that we could have. And so let's think about what are the usual suspects in these kind of conditions. So the first one is the discriminant, right? So we all know and love discriminant, and sort of one of the most important properties about it is that the Hermite-Minkowski theorem says that if you have number fields that share the discriminant, there are only finitely many isomorphism classes of those discriminants. Okay, so that's one. Now we have the regulator. But now, if you notice in my slide, it's not, there's a mistake with the colors. There's this sort of shadow here. The regulator is not, at least you could say, but wait, every complex quadratic number field has regulator equal to 1, right? So it's not, it wouldn't have the condition of being finite to 1, but under certain circumstances, it does. For example, if you have totally real number fields, totally real number fields, the regulator it is finite to 1. On the next one, the class number. So for that one, even the shadow is a little lighter, because for that one, we don't know anything about it, like how many number fields of a certain class number have. What I mean, we don't know for certain. We have a lot of conjectures, but we only know for complex quadratic number fields, class number 1 problem, there are finitely many of them. For real quadratic number fields, is conjecture there are infinitely many of them. So this is an invariant in that sense that I'm talking about, but just for certain conditions, okay? And conjecturally. Okay, so, but the point of naming these three guys over here is that how did we learn about them? Why are we talking? Why am I talking about these guys? How like, those are the numbers that are experiencing experience, but how did we learn about these quantities? And everything comes from the Minkowski embedding, right? So we sort of, when we take our classes in algebraic number theory, we learn about these guys and we learn their properties through the geometry of numbers. So what is the idea of the geometry of numbers? As you all know, the geometry of numbers, the idea is you take your number field and you put it in a nice way inside of an Euclidean space. What is the nice way? So I won't explain what the Minkowski embedding is. Just put all the conjugate of an element in there. It's sort of the ideas when you imagine the Gaussian integers and you put it in the plane, generalize that idea, okay? Now, that function is a map that is linear, right? So it's additive, it's Q-linear, but it's not only linear, but it's multiplicative, and multiplicative with respect to the product here point-wise. And of course, I'm lying because you would say, but wait, it is not multiplicative if your field is, for example, non-real, right? If you take the Gaussian integers and you put them inside of the R2, you don't have point-wise multiplication, but you have the multiplication of the complex numbers, right? And that function is multiplicative. Now, when you study that function, then by using sort of all the geometric properties of this space, this is an Euclidean space with an inner product, you prove this sort of three nice theorems. Which ones? This is a number, this is a number, and the discriminant has finite fibers, okay? And sort of the idea of the first two is that these, the ring of integers is a lattice inside of Rn, and the idea of the second one is that the units is a lattice inside of Rn minus one, okay? And all of the other things are sort of results about lattice and compactness. Okay, so, but someone could say that this is not the Minkowski embedding is not a coordinate-free version, right? You are making sort of a certain choice. What do I mean by a choice? You said, which embedding you put first? You could put second, you know, you just have sort of a permutation of the embeddings. So you could imagine what would be sort of the same coordinate-free version of this. And the coordinate-free version of this, what do I mean by this? Put this inside of this guy and take the inner product here and do the calculation in here without mention to the embeddings. And you have this coordinate-free version, as all you know, that is what is called the trace pairing, right? If you take the Minkowski embedding, you put inside of Rn, and you take the image of two vectors, and you want to take the inner product, the usual inner product. If you do the calculation, that is exactly the same as taking the pre-images of the two vectors and take x comma y and take the trace of x times y. So that's the trace pairing. Okay, so from that point of view, all the results that we mentioned before are results about the trace. You could translate them and are results about the integral trace. Now, there is another result that we love a lot about the discriminant. And what's the result? That the discriminant tells you about ramification, right? If you take I prime P and you see, okay, I want to see when there is ramification, right? So you have to look at these guys over here and you said the ramification is when these guys are bigger than one. And we learned that the ramification is something about the divisibility of the discriminant. But in reality, the ramification is not something that happens about the discriminant. The ramification is something that happens about the trace form. Let's think for a moment that here you only have just one prime lying over P. And you want to see, okay, well, I want to see if that prime is ramified. So I want to see if this number E1 is bigger than 1. That, of course, translates to say that this ring has nilpotence, right? So you say, okay, ramification translate at having nilpotence here. Now, how do you pick up if you have an nilpotent element? So multiplication by that element is a linear transformation. So being a nilpotent, that means that you have a linear transformation that is nilpotent, a non-trivial nilpotent one, right? And so you pick up the nilpotency of that linear transformation by noticing that when you multiply that number by any other number, you still get an nilpotent thing. So you have an element that element and the multiplication by any other element is nilpotent, right? So it's a matrix that sort of the trace of all its powers are equal to 0. And then you can work a bit and you realize that that is equivalent to say that the trace is degenerated, that all the eigenvalues are equal to 0. So now the way that explains a little complicated, but sort of the idea over here is just that the trace or finite fields is surjective. Okay, that's just sort of the point. And now that is not only about finite fields, but it's something about separable extensions. So to check if a prime is ramified is the problem about being non-degenerate the trace form when I look at as an element over ZP. Okay. So then I hope these initial slides were to convince you why the trace is really, really an important invariant that we just don't look that much. It gives us on one hand, sort of the theory about the finite fibers of the discriminant, gives the ramification. You can interpret the results about the geometries of numbers in terms of the trace. So what I'll talk about today are sort of the trace and other invariants that we also care a lot in algebraic number theory. So ones that you know, the discriminant you know very well, the shape I'll explain in a second, the integral trace form I sort of already did, the dedicated zeta function, something called the alpha invariance, the ring of Adels, and the absolute Galois group. I won't explain those guys, all of them here, but I will explain just the two of them in care, these two, with all the results. But something that I want to mention is, from all these invariants, the only one that is complete, the only one that characterizes a number field, it doesn't matter what number field it is, independent of any conditions of signature, discriminant, whatever, is the absolute Galois group. And what I mean an invariant, I mean this is an invariant in the category of topological groups, as the Adel ring is an invariant in the category or topological rings. The absolute Galois group is an invariant that's a result of Neukirch. That means that if you have two number fields that have the same absolute Galois group, then they're isomorphic. It's usually called the theorem of Neukirch and Uchida, because Uchida generalized it to say that the outer automorphism group of the absolute Galois group is trivial. Okay, so what is the integral trace? Again, so the integral trace is the pairing that I just described before, and the equality between two integral traces is defined, or the isometry class, as there are different ways to do it. It depends on the taste that you have for linear algebra. One definition could be, is just two number fields have the same integral trace. If there is a linear isomorphism between those, what I mean by that is just an isomorphism of abelian groups that respect the inner product. Okay, so what you do in linear algebra with product inner spaces. Another way to say it, it is just polynomial, homogeneous, symmetric of degree 2 with integer coefficients. And then the isomorphism is just given by, you say that two of these polynomials are the same if when you change variables, with an invertible change of linear variables, you get the same thing. Or equivalent, as in linear algebra, is just a matrix, which is symmetric, such that the equality between two matrices is the same given by the GLN action here. This is just the three translations of the same things, okay? So the first one is the free coordinate version of the second two ones. Okay, so examples. So I give you the rational numbers. So what is the integral trace? You pick a basis, and then you have sort of a matrix 1 by 1, that's the basis, and the polynomial is given by this. If I give you this quadratic field, then you pick your favorite basis. Everyone should have sort of kind of in their mind the favorite basis is given by 1, and this other number delta, which would be 1 plus this over 2. And then you have this matrix over here, or the polynomial. How do you construct the basis? Just in case you don't remember, you take trace of 1, 1. So the trace of 1 squared is equal to 2. The trace of 1 times the number here, that will be 1. And the trace of the number that makes the basis squared, that will be negative 11. Okay. There is another example, just in case you want to do some calculations while I talk. So you take the unique cubic field of discriminant 49. This matrix represents this trace form, also represented by this polynomial. Now, the shape, that's for those of you who have like a really, really geometric flavor in your hearts. So what's the shape? The shape was defined by David Ter in his PhD thesis under Lenstra, Hendrik Lenstra in Art Berkeley. And the idea was, you think about the Minkowski embedding. Now you put the ring of integers inside of Rn, okay? Now take the number 1. The number 1 is in every number field. So you take the image of the number 1. So that would be a vector in Rn. If the field is totally real, it will be the vector that has coordinates 1, 1, 1, 1, 1. Now that vector has an orthogonal space that's on a hyperplane, right? And now you take the image of the ring of integers inside that hyperplane. That image would be a lattice inside of the hyperplane, but would be a lattice of rank -1 because you cut the dimension by 1, okay? So let's do sort of an easy example to see what I mean. Let's take a very specific example that we can calculate. You take a cubic field, which is the field inside of the cyclotomic 7 field, okay? So it has degree 6, so the cyclotomic field will have degree 3. The real cyclotomic field has degree 3, is generated by this guy over here, eta 7. And you want to see what is the orthogonal complement to 1. So taking the trace, the orthogonal complement to 1 would be trace of x times 1 equals 0. So the trace of x equals 0. So you find out what are the elements of trace equal to 0. Since you have a very explicit description of the basis, the integral basis here, we know for these guys is generated by the power series of this one, the power basis of this guy. So you can find out that these two guys generate the trace 0 elements. Well, I'm not able to, okay. These two guys, U1 and U2 generate the basis. Now, you do a calculation, the trace of U1 score is 14, the trace of U2 score is 14, and the trace of U1, U2 is 7. In geometric terms, this is saying you have two vectors that the inner product is 1 after I divide by square root of 14, and the inner product between the two of them is a half. So you have two unitary vectors that have an angle of 60 degrees between them. And that is the lattice that you take. That is the hexagonal lattice. If you imagine that you have two vectors, magnitude 1, and the angle between them is 60. Okay, so that is sort of the shape of, oops, sorry. That is the shape of that cubic field. In general, the shape of a quadratic field just would be one-dimensional, so just would be Z. And that's it. So that is the shape, but that's one of the variants that people study a lot. Most people like Piper Harron, Rob Harron, and many of their corroborators have studied the shape. I have studied too. Okay, so let's see. Let's come back to the trace. What information can we recover from the trace? Right, so if you think about these examples, when I did the calculation of the trace of these three guys, so for example, the matrix here is 1 by 1, the matrix here is 2 by 2, and the matrix here is 3 by 3. That means that the trace, of course, recovers the rank. Another thing that the trace recovers, by definition, the discriminant of a number field is the determinant of each one of these matrices. So the discriminant is recovered by the trace. And another one that is maybe not that obvious, but if you do is the signature of this as a real quadratic form tells you what are the signature of the number field. What do I mean by the signature of the number field? This RK is the number of real embeddings, and SK is the number of complex embeddings. And the signature of a real quadratic form is what you learn in some sort of numerical analysis class or linear algebra class. You take your matrix, which is symmetric, you diagonalize it, and you check like in an orthonormal basis, and you check how many positive eigenvalues do you get and how many negative eigenvalues do you get. Okay, so for example, this one is a real when you diagonalize this one, you will get the identity. Is an easier exercise to see, and therefore this number here would be 0, and this number would be 3. So this is a real number field. Anyhow, so the trace will tell me the determinant, the discriminant, and the signature. So the natural question is, what else? What else can the trace tell me besides these two sort of easy invariants? Now, since we know that the discriminant is powerful enough to say that it has finite fibers and invariants, the trace will do the same. But what else? So baby steps. You should start thinking, okay, we'll see what happens with small degree number fields. For degree 2, the discriminant tell me everything, so nothing to do. So we'll see what happens with degree 3. And now when you deal with a problem and say, okay, cubic fields. So let's split cubic fields in several categories. You could do Galois versus non-Galois. Okay, and for cubic fields, and it's generally easy because the only Galois cubic fields, they have a very specific Galois group, right? The cyclic group of order 3. And those can also be described as the number fields, the cubic fields that have a square discriminant. So this sort of dichotomy here, I got split it in two things: square discriminant versus non-square discriminant, right? But there is another thing: is these guys here could be split in positive discriminant and negative discriminant. So for now, I'll just worry about sort of the positive case in general because the squares are positive, okay? Now, since I want to sort of separate the cases in sort of in a dramatic way to make things easier for me for my calculations, I would like to think about what is the opposite of being a square, a perfect square, so being a square free. Turns out that by doing some sort of research in like computational thing, we realize that after a while that those fields are completely characterized by the shape, okay? So, and the point here is, so again, so the idea, you start by analyzing what could happen. Dimension 2 is easy. Dimension 3, you split into cases, Galois versus non-Galois. The non-Galois cases is sort of the square free opposite of being completely square the discriminant. And then you investigate what happened in those cases. Now, I was able to prove a decade ago that the shape is a complete invariant for those fields. And sort of the tools to do that are sort of the idea of the class groups defined for cubes that Manjul defined. And the nice thing that we have sort of a really, really easy way to parameterize cubic rings. Using that sort of tools, one like have to now work on it and then prove that theorem over here. And the last sentence that says that the trace is a complete invariant is because in general, for real number fields, the trace is stronger than the shape. That means that if you have the same trace, we'll have the same shape. And therefore, since this shape here is a complete invariant for cubic fields, then the trace is a complete invariant for cubic fields. This is not always an equality in general, so it could be a little different. Now, again, by a computational playing a little bit, I conjecture in 2012 that this is the same behavior should happen for quartic fields. Now, what I should say, what do I mean by quartic fields and the same behavior? So I should translate positive fundamental discriminant to what really happened, and positive fundamental discriminant in cubic fields will translate as square totally real quartic fields of fundamental discriminant. So that's a conjecture, so I'll let it there. Now we move on to what happened then with the Galois case. So the square free case in cubic fields we did for positive ones. Now, if you think about Galois cubic fields are sort of easy because you have a lot of structure given by the Galois group, and at the same time, there is not much complication because 3 is small. And in that case, one can prove that if the d squared is the discriminant of the number field, then the integral trace is basically a polynomial given only by d. I'm sorry. A polynomial only given by the number d, okay? And there's this sort of, again, a dichotomy here presented in the sense that there is a difference between the field is completely ramified, it has wide ramification, or the field it does not have wide ramification. But it's not that important to stress it here. The point is that for cubic fields, you know that the trace is completely determined by the discriminant in the Galois, and that this form over here appeared in the description, okay? And this form is again the hexagonal lattice that I showed you in the example before. So, like when you think about this example and you realize what happened for quadratic fields, the shape is just easy because it's one-dimensional form, and up to scalars is just x squared. But this is the root lattice A1. This is a lattice. There is something called the root lattice AN, and there's sort of a nice description. In the case of 2 is this one, and in the case of 1 is x squared. So what is happening here is that there is a similarity what happened in cubic cases and quadratic cases for the Galois thing, right? So then you start thinking, okay, but 2 and 3 are primes. Maybe there is something going on, right? So what is what I mean by this? So in the case of degree 2 and degree 3 Galois extensions, the trace doesn't tell you anything beyond the discriminant. So this is a good thing. You said, okay, now I have a theorem to hunt. I'm gonna after this theorem, but then unfortunately, like 40 years before, someone proved the theorem you wanted to prove. And it is that if you have 2 number fields of degree P that are Galois, then the trace and the discriminant, the trace and the discriminant are equally strong as invariants. Now, the way that they do the proof is that they sort of realize that for degree P number fields, this is equal to a very, very specific sort of matrix or very specific sum of module But they didn't, at this point, they didn't analyze what happened with the shapes. The nice thing about the shapes, and when I sort of start thinking about this, I realized that, that one could generalize the result of cubic fields and quadratic fields to general degree P number fields that are Galois of degree P. And it turns out that in that case, if you have a number field of degree P, the shape is AP minus 1 or AP, or the dual of AP minus 1. This is a nice thing. And you will say, but what happened with cubic fields? The thing with cubic fields and quadratic fields is that A2 is isomorphic to its dual. And A1 is isomorphic to its dual because it's the same, obviously. Okay, so this is sort of a nice theorem that we could sort of at least prove by observing what happened in smaller degrees. But now, when you start thinking about 2 and 3, you ask the following question. Wait, they are also integers. They are not only primes. Okay, so you start wondering, could we do it the same? And then, so this is, I proposed this problem to my former grad student and sort of my former PhD student, William Bolaños, and then we were able to prove that in fact, it is not about being 2 and 3 being primes, it's about that the two number fields are cyclic extension. Now here we have to use that there is no wild ramification in our fields. We need sort of a controlled ramification. And the idea of doing these proofs is that there's a combination of many things. And sort of a principal idea is having a billion number fields, you can put it inside of cyclotomic fields, but if cyclic ones behave very, very well with respect transporting the trace. So the first step to prove this theorem would be you take n to be a prime power, and you assume that the conductor of your field, that your abelian field, is prime. So basically what I'm saying is this guy is inside of a cyclotomic extension of conductor prime. This is prime. And then for those ones, as you see, we have a lot of control over the situation of the ring of integer of these guys, and one can prove that the integral trace here has sort of a nice behavior in terms of the Galois group as a quadratic module with some specific form, and you can transport this form to a quotient form that do the same for these guys over here. So in particular, you could do that for those guys, and in general, you have to do a lot of pasting and a lot of working with Hermitian forms and circulants and a lot of stuff, but that's sort of the basic idea. And then to do the shape, we can also do the same thing about the shape as we did before, but in this case now we can only do it for real number fields. And you also have a very, very explicit description of the gram matrix of the shape in terms of some invariants. And this generalized these lattices, the root lattices, and the expressions are really, really messy and complicated. But that's sort of one result. So at this point you could say, okay, so we analyze what happens with cyclic number fields. So we analyze the Galois structure a lot. And we didn't get something amazing in the sense that we got an invariant, we have the description explicitly, but it's not better than the discriminant. It have exactly the same power that the discriminant has as a term of invariance. So maybe you're a little disappointed that in this situation you don't get what happened with the cubic fields over square free discriminant and positive discriminant. So you would like to see, okay, so what else could we do? And you start thinking, okay, so I have quadratic forms, the traces, and I want to see when they're isomorphic. So what do you know? What have you heard about that? And there is a very, very, very famous result we all seen at some point in our lives. This is the local global principle for quadratic forms, right? So we said, okay, two quadratic forms over Q are isometric if and only if they're isometric over every completion. And checking that quadratic forms are isometric over completions is easy, right? That is sort of the situation that happens, what I told you about the signature, thinking what happened with the real numbers. Is sort of, that's checking over the real numbers is easy. You only check how many positive eigenvalues you do, how many negative eigenvalues, and checking over the p-adics is easy. Now, so the formal question would be, okay, so let's assume that you have two number fields and their traces are the same. They're locally the same for every p. Does it follow that they are the same? And then sadness, the local global principle is not generally valid for integral quadratic forms. You know that it's valid for rational quadratic forms, but there's this very, very famous example that says, okay, It is not that these guys are equivalent over every ZP, but that obviously not equivalent over Z, because here you represent the number 1 and here you cannot. So then what do you do? So when you encounter a problem like that in math, you said, okay, I wanna use the local global principle, but the local global principle doesn't work for integral quadratic forms. So what can I do? And you said maybe for the ones that I want, maybe it works. Or maybe I can force it. I could say, okay, I'm gonna take certain number of fields and see for those ones, how can I make the local global principle work for me? So there's the notion of the genus. So I remind you, the notion of the genus, you have 2 integral quadratic forms, right? You can imagine those as polynomials or matrices or lattices. And you say, if they are in the same genus, if they are locally isometric over every ZP. Okay, so that's the notion of the genus. And there's the notion of isometry, if they're isometric over Z. Of course, if they're isometric over Z, they will be isometric over ZP. The same matrix that use the conjugation over Z will work over ZP. Now there is a notion in between, which is called the spinor genus. Now, I don't have to explain it very well, this notion, but the point is that if you have a quadratic form, you take the automorphism group of the quadratic form. What is the automorphism groups? Think about in terms of matrix, are the matrices that U times A times U transpose are equal to A. So the thing that fixes by the action. Now that group is not only a group, but if you think about it, it's given by some polynomial equations, and with some polynomial equations with integral coefficients. So this is an algebraic group over Z. And what is happening when you want to define the genus, the isometry, and the spinor genus is that the genus is taking the adelic points of that algebraic group and checking certain orbit. The isometry is taking the rational points of the point, and the spinor genus is taking certain subgroup given by the kernel of the spinors norms of these adelic points. Okay, so that's sort of the idea. It's nothing crazy. And there is a very nice theorem of Eichler that says that the genus and the isometry are the same under certain conditions. What conditions? Dimension 3. That's not bad for us because we care only from dimension 3 and up. And the second condition is that the form has to be indefinite. Indefinite means that it is indefinite over the real numbers. Okay, so it has at the same time positive eigenvalues and negative eigenvalues. That will translate into our interest, as we can, if we want to use that, we need non-totally real number fields. Okay, but we still have the problem about genus and spinor genus. We need sort of the condition of genus and spinor genus to see what happens. So if we want to use the local global principle, we need to study when the genus and the spinor genus of the integral trace is the same. And that's why we get to the idea that we get to the following theorem. If you have, I erased one of the theorems that I cared, but what, again, I tell you. So the point is that I proved it was around 2015 too, that the genus and the spinor genus of the integral trace is the same for any number field of dimension at least 3. Curious fact, is not true for quadratic fields. For quadratic fields, there is an infinite, there's a positive proportion of fields for which the spinor genus is not the same as the genus. Anyhow, so we know that the genus is the same as the spinor genus. Therefore, the genus is the same as the isometry class because of the theorem that I showed you before from Eichler. And those only work for non-totally real number fields. So we have sort of the theorem of classification of the integral trace for non-totally real number fields. So if you have 2 non-totally real number fields and you want to see when the traces are isometric, so first you need the necessary condition, the discriminant are equal and the signature are equal. And then we need the condition on the genus. And for the condition of the genus, you actually only have to check what happened with primes that divide the discriminant, odd primes. And if there are, for example, 3 primes that divide the discriminant, 3, 5, and 7, you only have to check 2 of them. And what is the condition that you have to check? This sort of weird condition over here. That means you have to check the Legendre symbol of these numbers that I call the alpha invariants that I define over here. So, so again, where is this coming from? This is coming from the idea of the genus, the spinor genus, and to check the genus, you have to check all these numbers, and these numbers, they just sort of fall into my lap when studying the genus of the quadratic form. Now, these numbers are defined in terms of the EIs are the usual ramification invariants, the FIs are the usual residue degrees, and UP is a number defined for every P, which is U2 is equal to 5, and UP is the first non-quadratic residue mod P. Like if I take numbers from 1 to P minus 1, take the first non-quadratic residue. So I describe that as the generator of this group, the first generator of that group. Now, there is something that I should point out. Notice that I say tame. Okay, why the condition here about tame? Because checking the genus is something about locality, right? Being something local. And I have to check local thing about number fields. So I go to local fields. And the problem with local fields are, and this is one of the things that the name is very adequate, wild versus tame. When the ramification is wild, those fields are wild. They are difficult to work with. So it's sort of hard to see what's happening. So I was able to prove the conditions in the tame number fields, but maybe you could do more. So this theory could be improved. The only thing that you need to know is sort of a good behavior of wild local fields. Okay. And now coming back to the sort of the case that I didn't mention in cubic fields, that was, we mentioned sort of Galois, and then we mentioned positive discriminant, but I never mentioned what happened with negative discriminant. It turns out that for those guys, the trace is not an amazing invariant beyond the discriminant. Two number fields have the same trace if and only if they have the same discriminant. And how am I able to prove this for cubic fields when in my previous theorem, it was sort of a little restricted condition? Because as I mentioned, the thing about the trace, and it becomes difficult in wild extensions. But if you have cubic fields, the only primes that could be wild are 2 and 3. So therefore, the difficulty in this problem for cubic fields would be trying to see what happened with cubic extensions of Q2 and cubic extensions of Q3, but those are finally many, and then you can just sort of work it out what happens with them, and then you obtain this sort of nice result about the trace. Okay, so a summary of what we got until this point. So what does the trace tell you? So for non-totally real number fields, sort of you have that the trace is completely given by the discriminant, the signature, and what I call the P signatures for finally many primes, those primes that are ramified. And the way that we got there was by analyzing the spinor genus and the genus of the trace and using this theorem on spinor groups on indefinite forms. Now, then we analyze what happened with cyclic number fields, and for those, the trace is not better than the discriminant, at least for tame, and the tools there were something about abelian number fields, so Kronecker-Weber, and a lot of things on Hermitian forms and symmetric circulants on group rings. And then sort of the best possible situation in terms of how strong as an invariant it is, you have the cubic fields of positive fundamental discriminant, and the tools there were that allow us to prove things were coming from parametrization of rings and higher class groups defined by Bargava. So now you said, okay, so in terms of a complete invariant, the one that I would like to generalize is this guy over here. Real cubic fields of fundamental discriminant. So the question is, can we do it? So computation, it seems that when I did the calculations, that for quartic fields, the same should be true as I mentioned before, at least I mentioned for the shape, but in general, we don't know. Now, in here, you start thinking, okay, so the tools that appear in nature, can we apply any of the tools that we have? Unfortunately, for higher dimensions, at least for dimensions bigger than 5, we cannot apply any of these tools over here. Here, non-totally real, so we care about real fields, so nothing. Here, we are talking about the structure of fields that have, are Galois, and they're abelian, they're cyclic, so there is nothing that you could generalize if you want to do it for an arbitrary number field. And in fact, if a field has fundamental discriminant, is a theorem of Takeshi Kondo that the field has Galois group Sn. So it's quite the opposite to what happened here. Okay, so then you need sort of a new way to see these things, a new tools. Now, fortunately for me, I met this is a former grad student of mine, Carlos Rivera Huaca, and then with him we were able to actually generalize what happened for cubic fields. For cubic fields, for totally real number fields, it doesn't matter what is the degree, the integral trace is a complete invariant. okay? Now, and this, it requires a new tool. And this is not the full theorem, but I will have to explain so many things and details. It is actually not something really about fundamental discriminant. It's more about Sn number fields. So there are some conditions that if you have two totally real Sn number fields, then the trace is a complete invariant. If the bad primes, what I call bad primes are sort of the primes that appear in the discriminant that have higher powers, are small with respect to the degree. If the degree controls those primes, then still you have a complete invariant. In the case of fundamental discriminant, there are no bad primes, or the only one would be 2, and 2 is small. Okay, and sort of the new tool here is what we call Casimir invariant pairings on quadratic spaces. Okay, so this is sort of, it will be hard for me to explain what it is, but I'll just give you the flavor or what these invariants or what they are. So now, the point is you take a field of characteristic different from 2. Why? Because I care about quadratic forms, and you have to be a really, really brave person to do quadratic forms in characteristic 2. Okay, so you have a quadratic form. A quadratic form is just a vector space over K with a bilinear non-degenerated symmetric form. Okay, now what we did is, given any field extension of the field K, we endow this set, the set of linear homomorphism from B to E, with a structure of a quadratic form. And that structure of quadratic form is related to the quadratic form given originally in the space V. Okay. Now, what are the points of this map? Is that the association to V to this space is functorial from quadratic forms over F to quadratic forms over E. And now, one important point that I want to make here, you could say like, oh, but there is an easy quadratic form that you could put in that space. Assume that for a second that E is K. So that's the dual space, right? So I said, okay, I have V, and I could take a quadratic form of the dual, transporting sort of the quadratic form that I have on the original V, right? Transporting using that the quadratic form is non-degenerate, but this is not the quadratic form. It's a different quadratic form. So it's not something stupid. And the most important thing about the form, sort of the important thing is like, if V is an étale algebra, okay? And so you can imagine that this is a quadratic space using the trace pairing, then this quadratic space that we have associated by the thing that I mentioned above, it has an orthonormal basis, and the orthonormal basis is given by the K algebra morphisms from B to K set. Now, in the case that we cared, there are number fields. So what I'm saying here? What I'm saying is, you take a number field L, and you embed it, and you have the linear morphism from L to Q bar. And I'm saying is that this is a quadratic space, and the complex embedding of your field form an orthonormal basis of that quadratic space. So in particular, for example, this sort of construction tells you that the complex invariants are linearly independent. That's a theorem of the linear independency of characters, but it can be recovered from this sort of construction over here. Using this construction, we can work out what happens with Sn number fields and recover that result that we proved with Carlos. And actually, I think you can generalize even a little better if you have some conditions. So the nice conditions about Sn are just sort of some group theoretical condition so for example, every 1 point stabilizer on Sn is a maximal subgroup, but you can work out that for other permutation groups and get similar results. Okay, so I guess, this result will imply the veracity of the conjecture that I made in 2012, and I'm putting it here, even though it might seem obvious, but it is not. So the shape will, for quadratic fields, the shape will determine the integral trace, and then because of the theorem above, then you have the result about the conjecture. But we wrote a paper in which we gave a different proof, and the proof that we wrote is a proof based on the parametrization of quartic rings given by Bargava. Why did we write that proof if we already have this proof with this old result? Because it was just to put in a cohesive way what happened with cubic fields and parametrization of cubic rings and the trace, and now what is happening with quartic fields, parametrization of quartic fields and the trace. And it's sort of the same idea, So maybe in the future, when we have some sort of parameterization of n rings, you could have also the shape over there and work it out and to see some sort of similar results. Okay, so into the next invariant. So zeta function. The Dedekind zeta function of a number field is as Robert Schneider mentioned in his talk, is you should see it and feel some warmth in your heart. It is a nice invariant, so I won't explain the details, all of you know. And sort of, it is an arithmetic invariant in the sense that just by the Euler product is giving you already a lot of arithmetic information of the field, right? Or at least, yeah, so it's telling you basically that the ring of integers is a residually finite Dedekind domain. That means that, that means what it means, you probably know. So every ideal is product of maximal ideals in a unique way, and every ideal has a finite index, every non-trivial ideal. Okay, so to arithmetic invariance. So one thing that we learned about the Dedekind zeta function that we learned very early in our classes in analytic number theory, or algebraic number theory, is the class number formula. I like to call it class number formula 1 and class number formula 2. Maybe class number formula 2 is not, I don't know why it's not that popular. Remember when I took these classes, no one told me right away, but I think both of them are very important. And as you know, the zeta function, it has the analytic continuation to a meromorphic function, the whole complex plane. It has a single pole at s equal 1. And the residue is given by this number over here. I think I already mentioned all the quantities here, but this wk is the number of root of unities in the field. And the second class number formula is telling you that the zeta function has a 0 of order the unit rank, the rank of the unit group, and sort of what I will call, it's not the residue, but let me use the name. The residue at that 0, that order, is given by this number over here. So just by looking at these two formulas, you know that some information that you could get from the zeta function already is that the two number fields that have the same zeta function will have the same number of complex embeddings, right? Why? You could do the quotient between these two numbers. So a lot of the stuff cancel out, and you will get sort of a transcendental number. You get pi to the something, right? And then there's something in the power of pi, you will be able to recover it. But you could get way more information. So the question is, okay, what can we obtain an information of our number field coming from the zeta function? And so it turns out you can get a lot. So it deserves a name. Two number fields are arithmetically equivalent if they have the same zeta function. That is exactly the same if you think about zeta functions as counting functions and a number of ideals as having the same number of ideals of a given norm. This checking that two number fields are arithmetically equivalent, you only have to check it for ideals of norm prime power. That's just because taking the norm of an ideal is a multiplicative function, and every ideal is product of prime ideals, and prime ideals have power prime norms. Okay. Now, when is the zeta function a complete invariant for a number field? So this is a question studied by Perlis. So he calls the terminology that he uses is solitary number field. So solitary number field is a number field such that the zeta function is a complete invariant for it. Perlis was able to prove that if you have degree up to 6, then the zeta function characterizes the field. Or if the Galois closure has Galois group, either the alternating group or the symmetric group, then the same happens. Now, in degree 7, he was able to prove or to exhibit a couple of number fields that have the same zeta function, but they are not isomorphic. And is a result of, I'm not sure whom, that if two septic number fields have, that are not isomorphic, have the same zeta function, then the Galois closure must have Galois group, the simple group of order 168. So that's sort of one of the results that we have of these guys. And Perlis also proved that the following things are completely determined by the zeta function: the degree, the signature, the discriminant, the Galois closure, the Galois core. Now, if you don't remember, or you don't know what is the Galois core, and you remember what is the Galois closure, just reverse all the arrows in the definition, and that's the Galois core. The unit group, in particular, since the torsion of the unit groups are roots of unity, then you have the same root of unity, and class number times regulator. Now, the number 7 here is like, you first prove from 1 to 6, and then number 7 is what you get left out in the class number formula, if you remember the residue of the class number formula 1. Now, you would imagine that maybe actually the class number is determined by the zeta function or the regulator, but in fact, it is not the case. The Smith and Perlis in 94, they found examples of degree 8 number fields in which they have the same zeta function and they have different class numbers. So how did Perlis arrive to these kind of results? So if you take a prime and you call the arithmetic type of the prime in a number field the tuple given by the residue degrees, and you put it in ascending order, so just to have some sort of labeling. So that's going to be the arithmetic type. And then it's a sort of a formal multiplication, a formal definition. The zeta function is, you have this product over here, the Euler product. And now for a prime P, a rational prime, you just associate together all the primes in K lying over P. So you can write that formula like this. Okay. And then you compare. And then you compare, and what you get is sort of combinatorial identity, and that combinatorial identity will tell you that the FIs, of course, that determine the ANs, and the AP to the M's determine the FIs. So the first result that Perlis proves, that is sort of his famous paper, is that two number fields are arithmetically equivalent, so they have the same zeta function if the arithmetic types are the same for almost all prime, and if so that is the obvious condition from the previous slide. And the new condition is that if certain groups are quasi-conjugated in another group. So what do I mean by this? So take K and L, your number fields, take the compositum and take the Galois closure of the compositum. So that's N, let's call it that, the number field, the Galois compositum. And that number field has some Galois group and call it G. Okay, that's perfect. And then what Perlis was able to prove, it was to give a group theoretical condition that says that if the two groups H1 and H2 corresponding to the number fields K and L are quasi-conjugated, then the zeta functions are the same. Quasi-conjugated, the way that Perlis phrased it is as follows. You take a conjugacy class in the group G intersected with the group H1, count how many elements do you have there, do the same thing for H2, and if these two numbers are the same, then the arithmetic types are the same, therefore the zeta functions are the same. So what is the idea? The idea is like, if you want to know what happened with the prime and the factorization, right? So if you remember, again, your basic number theory for Galois fields, so when you want to factorize the prime, there is sort of a certain decomposition as a permutation thing, and it depends on the Galois group. Okay, so if that is the Galois group, is if the number field that you take is Galois, but if it's not Galois, you could do something similar. You have to work a little harder, and it becomes sort of a notion of checking what happened in the Galois closure. And then Perlis was able to prove that, knowing the thing about the arithmetic types. Okay, now sort of if you're a fan of representation theory, this could be saying in a better way. It's saying that if you take the trivial representation of H1 and you induce it to G, that's the same as the trivial representation of H2 and induce it to G. Or if you are more like a combinatoric person, this is what is saying that the actions of G on G over H1 and the action of G on H2, so what is the action? The usual action of the residue classes of groups are Q isomorphic. Okay, so that's the condition. Now, you said, okay, this is very nice, but a lot of people in number theory are very geometric in their mind, right? And we say, okay, this is not, even though this is very cool, it would be nice to have a geometric interpretation of this result and to give it in sort of a general context, right? So what's sort of the most famous one. So there are many famous L functions in number theory, but from antiquity, let's say. So you have the Dirichlet series, the zeta functions, and the L function of elliptic curves. And those are functions that are completely geometric. And geometric in the sense that they are constructed via sort of the geometry of elliptic curves, right? This is via the Galois representation given by the TED module, okay? So you have your elliptic curve, you have the Tate module, right? You choose a nice prime. You could basically choose almost any prime, but choose one of your favorite primes. And then so you have the representation of the Galois group on the action on the torsion, right? And what we know from the isogeny theorem is that the functions are completely determined by the representations, right? And the representations are completely determined by the isomorphism class of the Tate module, and at the same time are completely determined by the FP points of the curve, the number of FP points of the curve, but at the same time are completely determined by the pth coefficient of the L function. Now, why am I making a stress about the pth coefficient? If you think what happened with the zeta functions, what we did is that the zeta function is not determined by the pth coefficient, but for every prime by all the powers, okay? So this is kind of way better than what we have over there. So you wonder, okay, so could we have something of the same sort? What would be the analog result for the zeta function? First, you need that the zeta function play the role of the L function of the curve. So you said, okay, I want the zeta function to be sort of the L function of certain curve, of certain Galois representation. The representation of the Tate module should be replaced by some representation, Galois representation that depends on the field. The Tate module should be replaced by some module. Okay, this is tautological in terms of representations. And the number of FP points on the curve should correspond on the number of FP points on the curve. But what is the curve? Spec okay. And then, okay, so this is what we need. And what is what we want, right? So what we'll like to have is a theorem of the sort, the same theorem, just copy and paste what we have. So the representations are conjugate, there is an isomorphism of the Galois modules, the pth coefficients are the same, and then, okay, the counting the points and the zeta functions are the same. Here, these are not typos here. I chosen to have 1 and 2 because those are sort of the important ones that I'm gonna sort of measure. And of course, these other two over here. So, and then it turns out that, okay, so we need a representation. How do we build up a representation of number fields? So I said, okay, so what is the first Galois representation that you learn in your life? So what is a Galois group? It's permutation of roots. And what is a number field? A polynomial and some roots. So what you do is, okay, so you take a number field. So instead of so the fancy name for the roots are the complex embeddings. Okay, and the Galois action in the complex embeddings is precomposition, and that give you a permutation of the roots. So that give you a permutation representation of the absolute Galois group, but Sn has a canonical embedding in GLN, right? And these give you a Galois representation, okay? And in terms of modules, that Galois representation is just take the set of embeddings with the action permutation or precomposition, the set of roots, okay? And then you have a theorem. So the theorem that we want is the one that we have. So this is sort of tautological about Galois representations. So what we get here, so the new thing, it is that then it is not new, but this point of view give you new things that the zeta function is equal to, is determined by what happened with the pth coefficients, okay? But it turns out that this result was already known, of course. But it was phrased in a different way. It was phrased in a way that the number of ones, the residual ones appear in the composition type is equal in both fields. This is exactly the same to say that these two guys are the same. But the good point about this is that we recover some previous result in a different way and in a simple way. Here, to prove this result, you need a lot of messy combinatorics with matrices and a lot of stuff. Here, you recover this in a sort of a nice, concise way, and you start thinking, okay, so can we recover more stuff that was previously known? Now, what is sort of the whole idea here? So the whole point about the L functions with the elliptic curves was like I think this was usually called the Eichler-Shimura relation, the basic one. Is basically the characteristic polynomial of Frobenius is x squared minus AP plus P, right? That's a nice thing about elliptic curves. And that translation, so the Eichler-Shimura relation for the zeta function is that the characteristic polynomial of Frobenius is this very nice polynomial over here. So you have the translation of the Fi's, okay? So now you could reduce all the results of Perlis and all the results from all these people in working on zeta functions of number fields in terms of the Galois representation. So for example, I'll give you the easy ones to explain right now. So the degree of representation is the rank of the number field. The number of real embeddings is the trace of complex conjugation. The discriminant of the number field in absolute value is the conductor of the representation. The Galois closure is the fixed field by the kernel of the representation. So everything could explain in those terms. Okay, so you said, okay, but so good so far, but is there anything new that you can get with this point of view? Because even, I mean, the new thing is, okay, we have like a prettier presentation at what we had before, but can we get anything new? And remember, one of the theorems of Perlis is that these two guys are the same, these are equivalents, if the arithmetic types are the same up to Dirichlet density, a set of Dirichlet density 0, right? And then using sort of an analogy of these results and in terms of counting points on curves, one can improve that to say that two number fields have the same zeta function if the set of primes in which the arithmetic types are the same have density bigger than this number over here. So in Perlis results, you need the density to be 1. Here you could have actually a set of density positive in which the guys a priori differ and still you have arithmetic equivalence. I should mention that even though the bound that I have is 1 minus 4n squared, I think that bound can be improved to 1 minus 2 over n squared. And actually I can prove the conjecture for n equals 2 and 3. And if I had a lot of energy, I will do it for n equals 4, but I have not. Okay, so just give me a couple of minutes and then, so I will sort of relate all of the invariants that I talked about just before. Now, let's come back to this centered thing, which was the easy representation, right? The representation that we have is the permutation representation of the roots in the number field. And what I did was put it inside of GLNC because Sn can be inside of GLNC. But how do you put Sn inside of GLNC? You put it as permutations of the identity matrix, of the column of the identity matrix. In particular, you're getting matrices that are orthogonal, and they're orthogonal over any field you want, even orthogonal over the integers, right? So you could have also done that Sn goes inside of the orthogonal group with algebraic coefficients, right? Now, what we did with sort of the interpretation of the permutation representation lives here. This is an element, this is a pointed cohomology class set. And what we did to Galois representation was to send it here, and that's the world of Galois representations. But one wonders what happened if I send it here. Instead of doing this horizontal way, I go into this vertical way, and there is an interpretation of this cohomology pointed set. So that's precisely the set of n-dimensional rational quadratic forms. So what this is saying is here, if I take with my number field, I get the zeta function in this universe, and here I get a quadratic form. So what quadratic form could it be associated to a number field? It would be weird if it was any other but the trace form, right? So this permutation representation and this cohomology set give you the trace, but it gives you the trace over Q. So the rational trace form. This is not as good as invariance and the integral trace form because it is not like there are infinitely many number fields with the same rational trace. Anyhow, so from the invariants that I mentioned today, so we have sort of, there is a connection between all of them. So the absolute Galois group is the strongest one, is already complete. So this, of course, is stronger than the adels. Now there's a theorem of Iwasawa that he proves that the adels are stronger than the zeta function. Okay, so if you turn number fields have the same adel ring, they will have the same zeta function. Okay, and what I just showed you is that zeta function actually, I didn't show you, but sort of give you an idea. The zeta function will imply that you have the same rational trace. A new invariant that I found, and again, when I was looking for the genus of the trace, are these alpha p numbers. For the genus of the trace, you only take the Legendre symbols of these numbers. But in general, if you take the sort of the whole list for every prime of those numbers, I can prove that this is a stronger invariant as the zeta function, and at the same time, that the ring of adels implies those invariants. Now, neither of these implications is reversible, and this is a special one. I found an example of two number fields in which all the alpha p's are the same except for p equals 2. And those number fields, they don't have the same ADEL. So this cannot also not be reversed. And sort of behind the scenes from all these invariants and all the time, the integral trace has appeared. The integral trace, it is not determined by any of those ones, just determined by this one, the complete one. There are cases in which you have two number fields that everything here is isomorphic, but the integral trace is not. And sometimes the integral trace determines all of them, because sometimes the integral trace is powerful enough. Sometimes you have some theorems in the zeta function determine the integral trace, but there is a huge connection between all those guys. So those are the sort of the invariants that I care about. And gracias.
Okay, let's thank Guillermo for a fantastic talk. Questions?
Yeah, I have a small question.
Let me do something, because yes, I don't know who's talking.
Yeah, yeah. Could you please go back to the slide where you are talking about the density, the conjecture 1 minus 1 by 4n square. Yes. So I'm wondering if you, I mean, if you make it 0 and here if you take a character twist, will it be true? Like if the density of primes where AKP equal to ALP is strictly greater than 0, then basically zeta KS will be a character twist of zeta LS. Do you expect that to be true?
So if I do it, so what you say is like, instead of taking, so a quadratic twist of the function would be sort of take the representation and tensor the representation by some dimension of one representation. And then you will have, so the point here is you will have to check. Yeah, I think so. Yeah, because it would be sort of like a twist, like what you do with an elliptic curve, that you twist the curve and you have like a twisted version of the curve. So here, this theorem, what is behind of this theorem is like you have two curves and you want to count sort of the FP points, so a la Serre, to see if the number of FP points, they will tell you what is the sort of the isogeny type of the curve.
Yes.
And I guess when you twist, what you do is you twist the two curves. And so now the question is the same question about other curves. So I guess the answer would be yes. This is what my intuition tells me, but I'm yeah, so yeah, that's a great question. I think the answer would be yes.
Yeah, thank you.
Further questions? So I'll ask a question. So there's this paper that you probably know by Altu, Shankar, Varma, and Wilson, studying D4 quartic fields. And what they show is that if you count them by conductor rather than discriminant, you get this very beautiful Euler product in the asymptotics. And I'm curious if the framework that you're developing predicts this type of phenomenon. Or if you think it can predict it.
It looks like the D4, you know, the discriminants of those ones are, so I really like, it would be, for these ones, no, it wouldn't work because the discriminant of a D4 field would be bigger, like 4 is too small to be able to compare with the discriminant. So I don't think, so something I could say maybe along those lines in the counting is, you could sort of apply this method with the trace and do, so there is this Siegel mass formula, right? So so the mass formula to count things, and you count sort of the genus of forms, and you count it with a weight, and the weight is given by the automorphism group, right? Now we were able to prove that the automorphism group for the genus, for the traces, are sort of trivial, and then you could use this sort of counting functions to be able to count number fields. But you so far I can count S3 number fields and S4 number fields. And so I recovered using these kind of results, some of the previous stuff that is been done before. But for D4, it will be hard. I mean, that's what, yeah.
Okay, thank you. Further questions?
There was something in the chat.
Was there?
Is it possible to count equivalence classes of zeta functions of bounded discriminant? Oh, so okay. So the question is like, let's say bounded degree. The problem is that we don't know. This is a group theoretical question. We don't know what groups have quasi-conjugated subgroups in general. It seems really hard to decide. So you see, for example, so what I mentioned about pair list, the result of being solitary up to 6, then there are number fields in degree 7 that have the same zeta functions, and then there are number fields until 8, but in 9 there is none, right? For 9 is also solitary, for 10 is also solitary, for 11 there are examples, and it is not clear what happened with those groups. So it is sort of a condition of a sort of a group theoretical condition that it seems hard to find out. You need a group in which you have these conditions, and I don't know if there is sort of a, no, I don't know. I'm completely sure there is no like a specific recipe for those kind of groups. So yes, so it will be hard.
Sorry, let's thank Guillermo again for a fantastic talk. Okay, so we're running a little bit over schedule. So as our last event for the conference, let's start the panel discussion at 2:45. So 7 minutes from now.